In the autumn of recent years, something unprecedented happened in the world of professional astronomy. For the first time in the modern era of digital record-keeping, major observatories around the world began quietly revising their published data on an interstellar object. Not once, not twice, but repeatedly over the course of several months. The object was 3I Atlas, and the numbers that should have remained constant were changing in ways that violated every principle of how astronomical data is supposed to work. Data doesn't lie. Data doesn't change its mind. Data doesn't develop second thoughts about what it recorded. Yet somehow, the fundamental measurements of our cosmic visitor, its brightness, its trajectory, its spectral signature, began shifting in official databases like sand dunes reshaping themselves in an invisible wind. This is the story of those numbers, and the questions that arise when the most objective science we know starts rewriting itself without explanation. When 3I Atlas was first detected by automated survey systems, it appeared to be exactly what astronomers expected from an interstellar visitor. The initial observations, logged with the precision that modern astronomy demands, showed an object moving through the inner solar system on a hyperbolic trajectory that clearly indicated its origin from beyond our sun's gravitational influence. The first measurements were straightforward, almost routine. Brightness readings placed Atlas at a magnitude that made it visible to medium-sized telescopes, but not dramatic enough to capture headlines. Spectroscopic analysis revealed a surface composition that seemed consistent with other rocky objects wandering the galaxy. Astrometric measurements tracked its position with a mathematical precision that allows astronomers to calculate orbits years in advance. These initial numbers were logged into the international databases that serve as the permanent record of cosmic discoveries. The Minor Planet Center, the official clearinghouse for solar system object observations, catalogued Atlas with the same systematic thoroughness applied to every asteroid, comet, and interstellar visitor detected by Earth's telescope networks. What made these first observations particularly significant was their consistency across multiple observatories. Independent measurements from facilities separated by thousands of miles showed remarkable agreement on Atlas's fundamental properties. Telescopes in Chile recorded brightness values that matched within statistical margins those obtained by observers in Hawaii. Radio telescopes in Australia detected the same spectral signatures reported by installations in Puerto Rico. This convergence of independent observations represented the gold standard of astronomical verification. When multiple facilities, using different instruments and operated by separate research teams, produce identical measurements of the same cosmic phenomenon, the astronomical community accepts those numbers as established fact. They become part of the permanent record, the foundation for future research, the baseline against which any changes or anomalies can be measured. The data was not only consistent, it was public. Following the established protocols of open scientific research, the measurements were published in accessible databases that researchers around the world could query and analyze. Graduate students incorporated the numbers into their thesis research. Amateur astronomers used the orbital predictions to point their backyard telescopes toward Atlas's position. Science journalists drew from the public data to write articles explaining our visitor's significance to curious readers. For several weeks, Atlas behaved exactly as the numbers predicted. It followed the trajectory calculated from those first observations with the clockwork precision that celestial mechanics demands. Its brightness varied according to the curves derived from initial photometric measurements. Everything about our interstellar visitor confirmed that the first data had captured an accurate snapshot of its physical properties and orbital characteristics. But then something began to shift in ways that had nothing to do with Atlas's actual behavior in space. The first hint that something unusual was happening came not from new observations of the object itself, but from subtle discrepancies that began appearing in the databases that housed its measurement history. Researchers who had downloaded Atlas data for their own analysis started noticing that return visits to the same databases yielded slightly different numbers. Not dramatically different. The changes were subtle enough that they might have been dismissed as typographical corrections or minor calibration adjustments. A brightness measurement that had been recorded as magnitude 12.4 appeared in later database queries as magnitude 12.1. An orbital element that had been calculated to 6 decimal places showed up with a different value in the 5th decimal position. spectroscopic data that had initially indicated one mineral composition began reflecting slightly altered ratios of the same elements. Each individual change was small enough to fall within the expected margins of measurement uncertainty. Astronomical observations always include error bars that acknowledge the limitations of instruments and the challenges of making precise measurements across interplanetary distances. The subtle shifts in ATLAS data remained within these technical boundaries, making them easy to explain as routine refinements rather than fundamental revisions, but the changes kept accumulating. Database entries that had been stable for weeks began showing new values with concerning regularity. Researchers who had been tracking ATLAS for their own projects started keeping private copies of the data, creating informal backup records that preserved the earlier measurements for comparison with whatever new versions might appear in official databases. This practice, scientists maintaining independent archives of data they couldn't trust to remain constant, represented something unprecedented in the digital age of astronomy. For decades, the international database systems had served as reliable repositories that researchers could reference with confidence. The idea that official measurements might change without clear documentation violated fundamental assumptions about how scientific record-keeping was supposed to function. The pattern of revisions began to reveal characteristics that made them even more puzzling. The changes weren't random corrections scattered across different types of measurements. Instead, they seemed to follow subtle trends that consistently pushed ATLAS's properties in specific directions. Brightness values tended to decrease in successive revisions. Orbital calculations were adjusted in ways that made the object's trajectory appear more ordinary, less dramatically hyperbolic. Spectroscopic data evolved toward compositions that seemed more typical of conventional solar system objects. It was as if ATLAS was being gradually transformed in the databases from an unusual interstellar visitor into something more mundane and predictable. The numbers weren't just changing, they were converging toward values that made our cosmic guest appear less remarkable than the initial observations had suggested. Observatory logbooks from the period show that actual new observations of ATLAS continued to be conducted according to normal research protocols. Telescopes around the world maintained their tracking programs, gathering fresh measurements that should have either confirmed the existing data or provided clear justification for any revisions. But these new observations didn't correlate in obvious ways with the database changes that were occurring simultaneously. Some of the most perplexing discrepancies emerged when researchers compared their own direct observations with the official database entries that were supposed to reflect those same measurements. Astronomers who had personally conducted photometric studies of ATLAS found that their submitted data appeared in databases with values that differed from what they had actually recorded in their instrument logs. This disconnect between personal observations and published data created an uncomfortable situation for researchers who depended on database accuracy for their work. How could they reference official measurements that they knew didn't match their own recorded observations? How could they build research projects on data foundations that seemed to be shifting beneath their calculations? The response to these discrepancies followed predictable patterns of institutional behaviour. Individual astronomers who noticed database inconsistencies typically assumed they had made errors in their own record-keeping or misunderstood the data processing procedures used by the archive systems. The possibility that the databases themselves might be unreliable was so contrary to established expectations that it was easier to question personal observations than official records. But as more researchers began comparing notes through informal channels, patterns emerged that were difficult to dismiss as individual mistakes or procedural misunderstandings. The database changes showed systematic characteristics that suggested coordinated revision rather than random error correction. Values were shifting in consistent directions across different types of measurements, as if guided by criteria that remained hidden from the astronomical community. Most unsettling of all was the absence of official documentation for these changes. Standard database management protocols required that any modifications to archived observations be accompanied by explanations that identified the reasons for revision, the sources of improved data, or the discovery of previous errors. The ATLAS data changes were occurring without these accompanying explanations, creating a record that looked increasingly like historical revisionism rather than scientific correction. As autumn progressed into winter and ATLAS continued its journey through the inner solar system, the database revisions continued with troubling regularity. The numbers that should have provided a stable foundation for understanding our interstellar visitor were becoming a shifting landscape of subtle alterations that made comprehensive analysis increasingly difficult. Researchers who attempted to publish papers based on Atlas observations found themselves confronting a moving target of reference data that could change between the time they submitted their manuscripts and the time those papers appeared in print. The very measurements that formed the basis for scientific conclusions about our cosmic guest were proving unreliable in ways that made systematic study nearly impossible. The astronomical community was witnessing something that challenged fundamental assumptions about the permanence and reliability of observational data. Numbers that should have remained constant were evolving like living organisms, developing new characteristics that bore only approximate resemblance to their original forms. In the careful language of professional astronomy, researchers began acknowledging these discrepancies in ways that avoided direct accusations while documenting the problems they were encountering. Conference presentations included diplomatic references to data variability and evolving observational parameters. Journal papers mentioned ongoing calibration refinements that made historical comparisons challenging. But beneath this measured professional language lay questions that struck at the heart of how astronomical research was supposed to function. If the basic measurements of cosmic objects could be revised without clear justification, what did that mean for the reliability of astronomical knowledge? If databases that had served for decades as trusted repositories could suddenly become unreliable, how could researchers maintain confidence in any archived observations? As 3i Atlas moved closer to its point of nearest approach to Earth, and then began its journey toward the outer solar system, the mystery of its changing data deepened rather than resolved. The numbers continued to shift in ways that suggested systematic revision, guided by criteria that remained hidden from public scrutiny. Something was happening to the observational record of our interstellar visitor that had no precedent in the modern history of astronomy. The most objective measurements that science could produce were proving surprisingly subjective, altering themselves in response to influences that left no clear signatures in the official documentation of database management procedures. What had changed during those months of subtle revision? The object itself, as it moved through space according to the laws of celestial mechanics, or the story we were telling ourselves about what we had observed in the darkness above our heads? To understand why the changing data on 3i Atlas represented such a profound violation of scientific protocol, we must first appreciate the extraordinary precision and permanence that characterizes modern astronomical record-keeping. This is a field built on the fundamental assumption that numbers, once verified and archived, become as immutable as the physical laws they represent. Imagine the night sky as a vast library where every point of light tells a story, written in the language of physics. Astronomers are the librarians of this cosmic collection, tasked with reading, recording, and preserving the information that streams continuously toward Earth from across the universe. Their methods have been refined over centuries to eliminate human error, institutional bias, and the countless sources of uncertainty that can corrupt observational data. The process begins with the telescopes themselves, instruments of such mechanical and optical precision that they can detect light that left distant objects millions of years ago and measure its properties with accuracy that would have seemed magical to earlier generations of stargazers. Modern telescopes don't just gather light, they dissect it, analysing every photon for the secrets it carries about the object that emitted it. Photometry, the measurement of celestial brightness, represents one of the most fundamental tools in the astronomer's arsenal. When light from a distant object enters a telescope, sophisticated detectors count individual photons and convert that information into numerical values that represent the object's magnitude, its brightness as seen from Earth. These measurements are repeatable, verifiable, and mathematically precise. The beauty of photometric data lies in its objectivity. A star of magnitude 5.2 will register the same brightness reading on properly calibrated instruments anywhere on Earth, whether observed from a mountaintop in Chile or a desert installation in Arizona. The numbers don't depend on the observer's interpretation, personal beliefs, or institutional affiliations. They represent direct measurements of physical reality, translated into mathematical language that can be universally understood and verified. Spectroscopy adds another layer of precision to astronomical observations. When starlight is dispersed through a prism or diffraction grating, it reveals a rainbow spectrum crossed by dark lines that serve as fingerprints of the elements present in the object being observed. These spectral signatures are as unique and immutable as DNA profiles. Hydrogen absorbs light at specific wavelengths that never vary, regardless of whether the hydrogen exists in a laboratory on Earth or in a star thousands of light years away. The spectroscopic analysis of cosmic objects produces data that is fundamentally unchangeable. If an interstellar visitor shows spectral lines indicating the presence of iron, silicon, and carbon in specific ratios, those measurements represent direct evidence of the object's chemical composition. The numbers don't evolve or develop second thoughts about what they recorded. They're permanent statements about the physical reality of distant objects, frozen in the moment of observation. Astrometry, the precise measurement of celestial positions and motions, operates according to equally rigorous standards. When astronomers track an object moving across the sky, they're recording its position relative to background stars whose locations have been mapped with extraordinary accuracy. These positional measurements allow for the calculation of orbital elements that describe the object's path through space with mathematical precision. Once an orbit is calculated from sufficient astrometric observations, it becomes a permanent mathematical description of how that object moves through the solar system. The orbital elements don't change unless the object itself experiences physical forces that alter its trajectory. Gravitational interactions with planets, outgassing from cometary activity, or collisions with other objects. In the absence of such forces, an object's calculated orbit represents an unchanging prediction of where it will be at any point in the future. The permanence of astronomical data extends beyond individual observations to the database systems that preserve and organize this information for the global research community. These archives represent humanity's collective memory of cosmic phenomena, repositories where the observations of thousands of astronomers working across decades are preserved in forms that future researchers can access and verify. The construction of these databases follows protocols that prioritize accuracy, completeness, and permanence. Raw observational data is processed through standardized pipelines that correct for known instrumental effects, atmospheric interference, and systematic errors. Multiple independent observations are combined to produce measurements with uncertainties calculated according to established statistical methods. The results are archived with detailed metadata that documents the circumstances of each observation, the instruments used, and the procedures followed. Once data enters these archives, it becomes part of the permanent scientific record. Researchers around the world can access the same measurements, verify published results, and build upon previous work with confidence that the fundamental data will remain stable and reliable. This permanence is essential for the cumulative nature of scientific progress, allowing knowledge to accumulate across generations of researchers who can trust that today's measurements will still be accessible and unchanged decades in the future. The peer review process adds additional layers of verification to astronomical data. Before observations can be published in professional journals, they must survive scrutiny from independent experts who examine the methodology, verify the calculations, and confirm that the results are consistent with established physical principles. This process filters out errors, identifies systematic problems, and ensures that only the most reliable data enters the permanent scientific literature. International coordination amplifies these quality control mechanisms. When multiple observatories around the world independently measure the same cosmic phenomenon and obtain consistent results, the astronomical community accepts those measurements as established fact. The convergence of independent observations using different instruments, different analysis techniques, and different research teams provides confirmation that transcends the limitations of any individual facility or methodology. This framework of precision, verification, and permanence has enabled astronomical discoveries that would have been impossible without absolute confidence in the reliability of observational data. Astronomers can detect planets orbiting other stars by measuring brightness variations of a few parts per million. They can map the large-scale structure of the universe by analysing the spectra of galaxies billions of light-years away. They can predict the return of comets decades before they become visible, based on orbital calculations derived from historical observations. But this entire edifice of scientific knowledge rests on the fundamental assumption that verified data remains constant. Numbers don't change their minds. Measurements don't evolve new characteristics. Archives don't revise themselves without clear documentation and compelling justification. The digital revolution has made astronomical databases more accessible and comprehensive than ever before, but it has also introduced vulnerabilities that didn't exist in the era of paper publications and printed catalogues. Digital records can be modified silently, without leaving obvious traces of the changes. Database entries can be updated remotely, instantly propagating revised values to users around the world. The very convenience that makes modern archives so valuable also makes them susceptible to unauthorized alterations that would have been impossible when observations were preserved only in printed form. Most astronomers work under the assumption that these theoretical vulnerabilities pose no practical threat. The scientific community operates according to principles of open verification and peer accountability that should prevent unauthorized data modifications. The reputation-based system of professional astronomy creates powerful incentives for accuracy and honesty, making systematic data manipulation not just unethical, but professionally suicidal. Yet the changing measurements of 3i Atlas revealed cracks in this system of checks and balances. Something was happening to verified, peer-reviewed, internationally accepted data that had no precedent in the modern history of astronomy. The numbers that should have provided a permanent foundation for understanding our interstellar visitor were proving surprisingly mutable. The implications extended far beyond the specific case of Atlas itself. If established astronomical data could be revised without clear justification or documented procedures, what did that mean for the reliability of the entire system of scientific record-keeping? If databases that had served for decades as trusted repositories could become unreliable, how could researchers maintain confidence in any archived observations? The problem was particularly acute because the changes to Atlas data were subtle enough to fall within normal measurement uncertainties, making them difficult to identify as obvious errors or unauthorized modifications. The revisions showed systematic characteristics that suggested coordination rather than random database corruption. But they remained within the technical boundaries that might be explained by improved calibrations or refined analysis techniques. This created a paradox that struck at the heart of how scientific verification was supposed to function. The changes were significant enough to affect research conclusions, but subtle enough to avoid triggering the alarm systems that were designed to detect database problems. They represented a form of data manipulation that was sophisticated enough to remain hidden within the normal margins of astronomical uncertainty. The institutional response to these discrepancies followed predictable patterns. Individual researchers who noticed database inconsistencies typically questioned their own record-keeping, rather than challenging the reliability of official archives. The possibility that verified scientific data could be systematically altered was so contrary to established expectations that it was psychologically easier to assume personal error than institutional deception. But the accumulating evidence of coordinated revisions began to challenge these comfortable assumptions. The changes to Atlas data weren't isolated incidents that could be dismissed as individual mistakes or technical glitches. They formed patterns that suggested systematic intervention by forces that remained hidden from public scrutiny. As more researchers began comparing their private records with official database entries, the scope of the discrepancies became impossible to ignore. The measurements that formed the foundation for scientific understanding of our interstellar visitor were being transformed in ways that violated every principle of how astronomical data was supposed to behave. The cosmic library that astronomers had spent centuries learning to read was proving less reliable than expected. The numbers that should have provided permanent records of physical reality were changing like words on a page that rewrote themselves when no one was looking. The question was no longer whether the data was being revised, but why such revisions were occurring and who had the authority to implement them. In the careful precision of telescopic measurements and the rigorous protocols of database management, astronomy had created systems that should have been immune to unauthorized alteration. Yet something was reaching into those systems and touching the data with invisible hands, transforming verified observations in ways that left no clear signatures of how or why the changes had been made. The permanent record of our encounter with 3i Atlas was proving surprisingly impermanent, subject to revision by influences that operated outside the established frameworks of scientific accountability and peer review. And in that realization lay questions that challenged fundamental assumptions about the reliability of the systems that preserve humanity's knowledge of the cosmos above our heads. The first documented case of systematic data alteration began appearing in the research notes of astronomers who had made the mistake of trusting their own memories more than official databases. These researchers had committed the apparently naive act of maintaining private copies of Atlas measurements, creating informal archives that preserved earlier versions of data that were supposed to remain constant. When they returned to official databases weeks later to verify calculations or extend their analysis, they discovered that their private records no longer matched the authoritative sources they had originally downloaded. The discrepancies were subtle, small enough to fall within normal measurement uncertainties, but systematic enough to suggest coordinated revision rather than random error correction. A photometric study conducted at an observatory in Chile had initially recorded Atlas at magnitude 12.4 during its approach phase. The researchers' personal files preserved this measurement, along with the detailed observational circumstances and instrumental calibrations that supported its accuracy. But when the same researcher accessed the international database 3 weeks later, the identical observation appeared with a revised magnitude of 12.1. The change represented a brightness increase of roughly 25%, significant enough to affect scientific conclusions about Atlas's physical properties, but small enough to remain within the margins of uncertainty that typically accompany astronomical measurements. More troubling than the magnitude of the change was the absence of any documentation explaining why the revision had been made or what new information had justified altering the original data. Similar discrepancies began surfacing in observations from facilities around the world. A spectroscopic analysis from an observatory in Hawaii showed mineral absorption lines that indicated one set of surface compositions in the researchers' original files, but appeared in official databases with subtly different ratios that suggested alternative interpretations of Atlas's chemical makeup. The changes were precise enough to require sophisticated understanding of spectroscopic analysis, yet no published papers or technical reports explained the basis for these revisions. Astrometric measurements presented perhaps the most unsettling examples of systematic data alteration. Orbital elements that had been calculated from careful position measurements began appearing in databases with values that produced significantly different trajectory predictions. The revisions weren't random adjustments that might reflect improved measurement accuracy. They consistently pushed Atlas's calculated orbit toward characteristics that made the object appear more typical, less dramatically hyperbolic, more consistent with conventional solar system objects. These orbital revisions created cascading problems for researchers who had based their work on the earlier calculations. Graduate students found that their thesis projects, built on trajectory predictions downloaded from official sources, no longer matched the orbital elements available in those same sources weeks later. Conference presentations that had referenced specific approach distances and velocity measurements were rendered obsolete by database entries that had evolved toward different values. The pattern of changes revealed characteristics that made them increasingly difficult to dismiss as routine calibration improvements or error corrections. The revisions showed temporal clustering, occurring during specific time periods rather than being distributed randomly across the months of Atlas observations. They affected multiple types of measurements simultaneously, suggesting coordination across different research teams and institutional boundaries. Most significantly, they consistently moved Atlas's observed properties toward values that made the object appear less unusual, less worthy of special attention or detailed study. Observatory logbooks from the period reveal another layer of mystery surrounding these data revisions. While official databases were showing evolved measurements, the original instrumental records maintained by individual facilities often preserved different values that matched the earlier versions researchers had saved in their private files. This created a disturbing disconnect between what telescopes had actually recorded and what appeared in the authoritative databases that were supposed to reflect those observations. Some of the most troubling discrepancies emerged when researchers attempted to trace the provenance of revised data back to its observational sources. Database entries that showed updated values often lacked the detailed metadata that should have documented when the changes were made, who authorized them, and what improved observations or analysis techniques justified the alterations. The revised numbers appeared with timestamps that predated the original observations, as if the databases were retroactively editing their own history. This temporal inconsistency violated fundamental principles of scientific record-keeping. Observational data should accumulate chronologically, with later measurements either confirming or refining earlier ones through clearly documented processes. The Atlas revisions seem to work backwards through time, replacing historical observations with alternative values that claim to represent what had always been recorded, despite contradicting the personal records of the astronomers who had made the original measurements. The geographic distribution of these data changes added another puzzling dimension to the pattern. Observations from certain observatories appeared to be more susceptible to revision than others, but the selectivity didn't correlate with obvious factors like institutional funding, political affiliations, or technical capabilities. Major facilities with excellent reputations found their Atlas data subject to the same mysterious alterations as smaller installations with limited resources. International coordination, which normally served as a safeguard against systematic errors or institutional bias, seemed to amplify rather than prevent the data revisions. When multiple observatories around the world had independently measured the same properties of Atlas and obtained consistent results, those convergent observations provided particularly attractive targets for systematic revision. Changing coordinated international measurements required more sophisticated intervention than altering isolated data points, but it also created more comprehensive transformation of the scientific record. The response of the astronomical community to these discrepancies followed predictable institutional patterns. Individual researchers who noticed database inconsistencies typically assumed they had made errors in their own record-keeping or misunderstood the data processing procedures used by archive systems. The possibility that official databases might be systematically unreliable was so contrary to established expectations that it was psychologically easier to question personal observations than challenge authoritative records. But informal communication networks began carrying reports of similar experiences from researchers at different institutions. Conference conversations included carefully worded discussions of data variability and evolving measurement standards that acknowledged problems without making direct accusations. Professional email lists carried diplomatic queries about best practices for version control in database management that implicitly recognized the reality of unauthorized revisions. These informal acknowledgements created a parallel information system where researchers could share concerns about database reliability without violating the professional norms that discouraged direct challenges to institutional authority. The astronomical community was developing its own version of samizdat, underground circulation of information that couldn't be discussed openly through official channels. Some researchers began implementing personal database management strategies that reflected declining confidence in official archives. They started downloading and storing local copies of all data relevant to their research projects, creating redundant archives that could serve as insurance against future revisions. They implemented systematic comparison procedures to detect changes between their private records and official databases. They began citing specific database access dates in their publications, creating temporal anchors that could document when particular values had been retrieved. These defensive measures represented a fundamental shift in how astronomical research was conducted. Instead of trusting official databases to provide stable, reliable access to observational data, researchers were forced to become database administrators themselves, maintaining parallel archives and conducting continuous verification procedures to ensure the consistency of their source materials. The workload implications were staggering. Professional astronomy had evolved toward increasing specialization and division of labor, with researchers focusing on narrow areas of expertise while depending on institutional infrastructure to provide reliable access to the broader database of human knowledge about the cosmos. The Atlas data revisions forced researchers to divert time and energy from scientific analysis toward database management tasks that had previously been handled by professional archive systems. More fundamentally, the need for these defensive measures violated basic assumptions about how scientific knowledge accumulation was supposed to function. The collaborative nature of astronomical research depended on shared confidence in common data sources. When those sources became unreliable, the entire system of peer review, verification, and cumulative discovery was placed at risk. The most unsettling aspect of the data revisions was their apparent sophistication. The changes weren't crude alterations that could be easily identified as obvious tampering. They required detailed understanding of astronomical measurement techniques, statistical analysis methods, and database management procedures. They showed knowledge of how different types of observations related to each other and how changes in one measurement would affect calculations based on that data. This level of sophistication suggested intervention by parties with professional expertise in astronomical data analysis. The revisions couldn't be explained as random hacking attempts or automated system errors. They required human intelligence, technical knowledge, and coordinated effort that could only come from sources with intimate familiarity with how astronomical databases were structured and maintained. Yet no official acknowledgement of these revisions appeared in the professional literature. No technical reports explained improved calibration procedures that might justify systematic changes to archived data. No administrative announcements documented database maintenance activities that could account for the observed alterations. The revisions were occurring within a framework of institutional silence that made their existence even more disturbing than their specific effects on Atlas research. As autumn progressed into winter, and the pattern of data changes became too obvious to ignore, some researchers began maintaining detailed logs of database discrepancies that documented the evolution of Atlas measurements over time. These informal archives preserved evidence of systematic revision that was disappearing from official sources, creating alternative records that might someday allow reconstruction of what had actually been observed versus what appeared in authoritative databases. But even these private documentation efforts faced limitations that reflected the scope of the problem. The researchers maintaining alternative archives had no way to verify that their own records were complete or accurate. They couldn't determine whether the discrepancies they were documenting represented the full extent of data revision, or merely the visible portion of more comprehensive alterations. They couldn't know whether their defensive measures were preserving authentic observations or simply different versions of systematically corrupted information. The data revisions had created an epistemological crisis that extended far beyond the specific case of 3i Atlas. If verified astronomical observations could be systematically altered without documentation or acknowledgement, how could researchers maintain confidence in any database entries? If the institutional systems designed to preserve scientific knowledge could become unreliable, what alternatives existed for ensuring the continuity and integrity of human understanding about the cosmos? In the quiet transformation of numbers that should have remained constant, the astronomical community was confronting a challenge that threatened the fundamental assumptions upon which their entire field was built. The permanent record of humanity's encounter with our interstellar visitor was proving surprisingly impermanent, subject to revision by forces that operated outside the established frameworks of scientific accountability and peer review. The cosmic library was rewriting itself, and no one could explain who held the pen. When the astronomical community could no longer ignore the systematic alterations to Atlas data, official explanations began emerging through the careful, measured channels that institutions use to address uncomfortable questions without acknowledging the full scope of the problems they face. The first category of explanation focused on instrumental calibration refinements. Observatories that had contributed measurements to the Atlas database began issuing technical reports describing improved understanding of their telescope systems, updated calibration procedures, and revised error analysis methods that necessitated retroactive corrections to previously published data. These calibration explanations carried the reassuring authority of technical expertise. They referenced complex instrumental effects like nonlinearity corrections in photometric detectors, systematic errors in astrometric measurements caused by atmospheric refraction models, and spectroscopic calibration improvements based on updated laboratory wavelength standards. The language was sufficiently technical to discourage detailed scrutiny from researchers outside the specific instrumental specialties involved. But calibration refinements, by their nature, should produce random corrections distributed around zero, some measurements revised upward, others downward, with no systematic bias in any particular direction. The Atlas data changes showed consistent trends that pushed the object's properties toward more ordinary, less remarkable characteristics. Brightness values tended to decrease in successive revisions. orbital eccentricity calculations were adjusted toward less dramatically hyperbolic trajectories. Spectroscopic measurements evolved toward compositions that seemed more typical of conventional solar system objects. This systematic bias was difficult to explain through calibration improvements alone. Instrumental errors are typically random, producing scatter around true values rather than consistent displacement in specific directions. The coordinated nature of the Atlas revisions suggested influences that operated according to criteria beyond simple measurement accuracy. The second category of official explanation involved orbital mechanics refinements. As more observations of Atlas accumulated over time, astronomers argued, improved orbital calculations naturally led to better understanding of the object's trajectory and physical properties. Early measurements, based on limited observational data, were necessarily preliminary and subject to revision as additional information became available. This evolutionary explanation had superficial plausibility. Orbital calculations do improve as more measurements become available, allowing astronomers to refine their understanding of an object's path through the solar system. The process of progressive refinement represents standard practice in astronomical research, where initial estimates are gradually replaced by more accurate determinations based on expanded datasets. But the Atlas orbital revisions showed characteristics that were inconsistent with normal refinement processes. Instead of converging towards stable values as more data became available, the orbital elements continued changing in ways that suggested ongoing adjustment rather than progressive improvement. The revisions often contradicted measurements that had been made weeks after the earlier observations, implying that newer data was somehow less accurate than older information. More troubling was the pattern of orbital changes themselves. The revisions consistently reduced Atlas's orbital eccentricity and approach velocity, making the object appear less dramatically interstellar and more consistent with objects that might have originated within the outer reaches of our own solar system. These changes weren't random improvements in mathematical precision. They represented systematic transformation of Atlas from an obviously interstellar visitor into something more ambiguous and less scientifically significant. The third category of explanation involved data processing improvements. Database administrators issued statements describing upgraded software systems, enhanced quality control procedures, and improved statistical analysis methods that had identified problems in earlier data processing pipelines. Previously published measurements were being retroactively corrected to reflect these technical improvements. These processing explanations appealed to the rapid pace of technological development in astronomical data analysis. Software systems for handling large datasets were constantly evolving, incorporating new algorithms and improved statistical methods that could potentially identify systematic errors in earlier analysis procedures. The retroactive application of improved processing techniques represented legitimate scientific practice aimed at ensuring the highest possible data quality. But the timing of these processing improvements raised questions about their relationship to the specific case of Atlas. The enhanced quality control procedures seemed to be applied selectively to Atlas data, rather than systematically to entire database archives. Other interstellar objects in the same databases showed no comparable pattern of systematic revision, despite having been processed through the same data analysis pipelines that had allegedly contained the errors now being corrected for Atlas. The selective application of improved processing techniques suggested criteria beyond simple data quality considerations. If the processing improvements were genuine enhancements that corrected systematic errors, they should have affected all objects processed through the same systems. The fact that Atlas received special attention implied factors beyond technical accuracy that influenced which data was selected for revision. Administrative explanations formed a fourth category of official response. Database managers issued statements describing routine maintenance activities, archive consolidation projects, and system migrations that had required temporary modifications to data access procedures. The apparent changes to Atlas measurements were attributed to technical glitches in database query systems, rather than alterations to the underlying observational data. These administrative explanations suggested that the data itself had never changed, only the ways that users accessed it through database interfaces. The discrepancies reported by researchers were attributed to temporary system problems, caching errors, or user interface bugs that had created the illusion of systematic revision when no actual changes had occurred to archived observations. but researchers who had documented the Atlas data changes had implemented sophisticated verification procedures that went beyond simple database queries. They had downloaded complete datasets, performed independent analysis of the raw measurements, and maintained detailed logs of their access procedures. The administrative explanations couldn't account for discrepancies that persisted across different database systems, access methods, and verification techniques. More fundamentally, the administrative explanations failed to address the systematic nature of the reported changes. Database glitches and interface errors typically produce random inconsistencies rather than coordinated alterations that consistently push measurements in specific directions. The pattern of Atlas revisions showed characteristics that were inconsistent with technical system problems and more consistent with deliberate data manipulation. The most sophisticated official explanations combined elements from multiple categories, creating complex narratives that attributed the Atlas data discrepancies to interactions between calibration improvements, orbital refinements, processing upgrades, and administrative changes. These multi-factor explanations acknowledge the systematic nature of the revisions while maintaining that they resulted from legitimate scientific and technical improvements rather than unauthorized alterations. These comprehensive explanations required considerable technical expertise to evaluate properly. They referenced specialized knowledge in multiple areas of astronomical research and database management, creating barriers to independent verification by researchers who lacked expertise in all the relevant technical domains. The complexity of the explanations made it difficult for the broader astronomical community to assess their validity comprehensively. But even the most sophisticated multi-factor explanations struggled to account for certain characteristics of the Atlas data changes. The temporal clustering of revisions during specific time periods suggested coordination that went beyond normal scientific and technical improvement processes. The geographic distribution of affected observations implied systematic intervention that transcended individual institutional boundaries. The consistent directional bias of the changes indicated criteria that operated according to principles beyond simple measurement accuracy. Most problematically, the official explanations failed to address the absence of standard documentation that should have accompanied legitimate data revisions. Calibration improvements should have been described in technical papers that allowed independent verification of the revised measurements. Orbital refinements should have been published with detailed mathematical analysis that demonstrated the superiority of the new calculations. Processing improvements should have been documented in software release notes that explained the specific enhancements and their effects on archived data. The lack of such documentation represented a significant deviation from established scientific practice. The astronomical community operates according to principles of open verification and peer review that require detailed justification for any changes to published observations. The Atlas data revisions were occurring outside these established frameworks, creating revised measurements that claimed scientific authority without providing the evidence that would allow independent evaluation of their validity. The institutional response to requests for additional documentation followed predictable bureaucratic patterns. Detailed technical information was described as proprietary to specific observatories or database systems. Comprehensive analysis reports were characterized as internal documents not available for public distribution. The specific personnel responsible for authorizing the revisions were identified as being unavailable for direct consultation due to professional obligations or institutional policies. These administrative barriers effectively prevented independent verification of the official explanations, while maintaining the appearance of legitimate scientific procedures. The explanations existed in a realm of claimed technical authority that discouraged detailed scrutiny while providing insufficient information to allow comprehensive evaluation of their validity. As the pattern of official explanations accumulated over several months, they began to reveal their own internal inconsistencies. Different institutions offered contradictory accounts of the same data revisions. Technical improvements that allegedly affected all similar observations were applied selectively to Atlas data alone. Processing refinements that claimed to correct systematic errors somehow produced systematic biases that consistently altered measurements in the same directions. These inconsistencies suggested that the official explanations were constructed after the factor rationalized changes that had been made for reasons that couldn't be publicly acknowledged. Rather than representing genuine accounts of technical improvements and scientific refinements, the explanations appeared to be institutional cover stories designed to normalize systematic data manipulation that had occurred for undisclosed purposes. The astronomical community found itself confronting a crisis of institutional credibility that extended far beyond the specific case of Atlas data revisions. If official explanations for database changes couldn't withstand careful scrutiny, how could researchers maintain confidence in the reliability of any institutional accounts of data management procedures? If the systems designed to preserve scientific knowledge were operating according to criteria that couldn't be openly acknowledged, what alternatives existed for ensuring the integrity of archived observations? The official explanations had attempted to restore confidence in database reliability by providing technical justifications for the observed changes, but their internal inconsistencies, lack of supporting documentation, and failure to address the systematic characteristics of the revisions had instead highlighted the extent to which institutional accounts of data management could become disconnected from verifiable reality. In the careful language of bureaucratic reassurance, official sources had acknowledged that changes to Atlas data had occurred, while maintaining that those changes represented legitimate improvements rather than unauthorized alterations. But the explanations themselves had become part of the mystery, adding layers of institutional obfuscation to data revisions that already violated fundamental principles of scientific record keeping. The question was no longer whether the Atlas data had been systematically altered, but whether official explanations could be trusted to provide accurate accounts of why those alterations had been made and who had authorized them to occur. In the space between official explanations that didn't quite satisfy and observed patterns that didn't quite make sense, a more unsettling possibility began to take shape in the minds of researchers who had watched their trusted databases transform without adequate justification. What if the systematic alteration of Atlas data wasn't the result of scientific improvement or technical error, but something far more deliberate, an organized effort to manage information that had become inconvenient for reasons that couldn't be publicly acknowledged? The hypothesis of intentional data manipulation carried implications that challenged fundamental assumptions about how scientific institutions operate. Astronomy had always prided itself on being a field driven by objective measurement and open inquiry, insulated from the political and economic pressures that might influence other areas of research. The idea that astronomical data could be systematically altered for non-scientific reasons represented a violation of principles that the entire field depended upon for its credibility and integrity. Yet the characteristics of the Atlas data changes bore uncomfortable resemblances to information management techniques that had been documented in other contexts, where institutional authorities had determined that certain types of knowledge posed risks to public order, economic stability, or national security interests. Consider the pattern of systematic revision that consistently pushed Atlas's observed properties toward more ordinary, less remarkable characteristics. This wasn't the random scatter of measurement improvements or the convergent refinement of progressive scientific understanding. Instead, it resembled what information theorists call normalization. The deliberate adjustment of anomalous data points to bring them closer to expected or acceptable values. Normalization techniques are commonly used in fields where maintaining public confidence requires managing the presentation of information that might otherwise generate alarm, panic, or disruptive speculation. Economic data is regularly seasonally adjusted to smooth out variations that might create false impressions of instability. Public health statistics are often presented in ways that emphasize long-term trends rather than short-term fluctuations that might trigger unnecessary concern. The systematic nature of the Atlas revisions suggested similar management principles applied to astronomical data. The object's brightness was adjusted downward, making it less visually prominent and reducing the likelihood that amateur astronomers might independently observe characteristics that contradicted official measurements. Its orbital elements were modified to suggest less dramatic interstellar origins, reducing its scientific significance and the attention it might attract from researchers seeking to study unusual cosmic phenomena. Most tellingly, the spectroscopic data was revised toward compositions that appeared more typical of conventional solar system objects. These changes didn't just affect technical measurements, they influenced fundamental scientific conclusions about what Atlas represented and whether it deserved continued intensive study or public interest. The selective application of these normalization techniques to Atlas data, while leaving other similar objects unaffected, suggested criteria beyond simple scientific accuracy. If the revisions reflected genuine improvements in measurement or analysis techniques, they should have been applied consistently to all objects processed through the same instrumental and database systems. The fact that Atlas received special attention implied decision-making processes that considered factors beyond technical precision. The timing of the data revisions provided additional evidence for intentional management rather than routine scientific improvement. The changes clustered around specific time periods that correlated with increased public and media attention to Atlas's passage through the inner solar system. As news coverage of the interstellar visitor intensified, the systematic alteration of its observational characteristics accelerated correspondingly. This temporal correlation suggested institutional sensitivity to public perception of Atlas's significance. The revisions appeared designed to reduce the object's apparent anomalousness precisely when that anomalousness was attracting attention from audiences beyond the professional astronomical community. The effect was to gradually transform Atlas from a dramatically unusual cosmic visitor into something more mundane and less worthy of special concern or continued investigation. The geographic distribution of affected observations hinted at coordination that transcended individual institutional boundaries. Data from observatories in different countries, operated by separate organizations with distinct administrative structures, showed similar patterns of systematic revision during the same time periods. This level of coordination would have required communication and agreement between institutions that normally operated independently, suggesting oversight by authorities with influence that extended across international boundaries. Such coordination mechanisms exist within the global scientific community through various professional organizations, funding agencies, and regulatory bodies that maintain influence over research priorities and publication standards. These networks typically operate through informal consultation and consensus building rather than formal command structures, but they possess considerable ability to shape how scientific information is presented to broader audiences. The possibility that these coordination mechanisms had been activated to manage the presentation of Atlas data raised profound questions about the autonomy of scientific research and the reliability of astronomical databases. If international networks of institutional authority could systematically alter verified observations when they became inconvenient, what safeguards existed to protect scientific integrity from non-scientific influences? Historical precedents provided disturbing context for these concerns. The astronomical community had previous experience with information management during periods when cosmic observations intersected with national security considerations. During the Cold War, observations of artificial satellites were routinely classified or altered to prevent disclosure of military capabilities. Ground-based telescopes that detected previously unknown objects in Earth orbit often found their discoveries subject to review by authorities who determined whether public disclosure served broader strategic interests. The procedures developed during that era for managing sensitive astronomical information had never been formally discontinued. The administrative frameworks, security clearance requirements, and institutional relationships that enabled classification of astronomical discoveries remained in place, available for activation when cosmic observations were deemed to pose risks to public order or national security. The systematic revision of Atlas data showed characteristics consistent with these historical information management techniques. The changes were implemented through established database systems using procedures that appeared legitimate on the surface. The alterations were subtle enough to avoid triggering obvious alarms, while systematic enough to achieve comprehensive transformation of the observational record. The timing and coordination suggested institutional planning and oversight rather than random technical improvements. Most significantly, the revisions were accompanied by official explanations that provided technical justification for the changes while avoiding discussion of the decision-making processes that had determined which data required alteration. This pattern of acknowledged revision combined with undisclosed authorization was consistent with information management procedures designed to maintain public confidence while serving institutional priorities that couldn't be openly acknowledged. The psychological dimensions of systematic data manipulation extended beyond simple information control to encompass more sophisticated techniques for shaping public perception and scientific understanding. Rather than simply suppressing inconvenient discoveries, the Atlas revisions represented a more subtle approach that gradually transformed anomalous observations into unremarkable measurements through incremental adjustment. This gradual transformation avoided the obvious fingerprints of censorship while achieving similar effects. Researchers who had initially observed unusual characteristics in Atlas data found their measurements systematically undermined by database revisions that made their conclusions appear overstated or inaccurate. The effect was to discourage continued investigation of anomalous aspects, while maintaining the appearance of legitimate scientific evolution. The technique was particularly effective because it exploited the natural tendency of researchers to trust authoritative databases over their own observations. When individual measurements conflicted with official archives, the psychological pressure to assume personal error rather than institutional manipulation made it unlikely that systematic data alteration would be recognized or challenged effectively. The implications extended far beyond the specific case of Atlas to encompass broader questions about the reliability of scientific knowledge in fields where discoveries might intersect with institutional interests. If astronomical databases could be systematically altered when observations became inconvenient, how could researchers maintain confidence in any archived data? If the institutions responsible for preserving scientific knowledge operated according to criteria that couldn't be openly acknowledged, what alternatives existed for ensuring the integrity of human understanding about the cosmos? The possibility that Atlas data had been systematically managed rather than scientifically improved represented a paradigm shift that challenged fundamental assumptions about how scientific institutions operate. The astronomical community was confronting the realization that their field might not be as insulated from external influences as they had believed, and that the data they depended upon for their research might be subject to manipulation by authorities with priorities beyond scientific accuracy. Yet the evidence for intentional data manipulation remained circumstantial, based on patterns and correlations rather than direct documentation of decision-making processes or explicit acknowledgement of non-scientific criteria. The official explanations, despite their inadequacies, provided alternative accounts that maintained the appearance of legitimate scientific procedures. The possibility of systematic cover-up existed alongside the possibility of systematic correction, with insufficient evidence to definitively distinguish between them. This ambiguity was perhaps the most unsettling aspect of the entire situation. The astronomical community found itself unable to determine with certainty whether their trusted databases represented objective scientific measurements or managed presentations of information that had been deemed suitable for public consumption. The uncertainty itself became a form of institutional control, creating doubt about the reliability of scientific knowledge while avoiding the obvious confrontation that would result from explicit censorship. In the careful balance between revelation and concealment, between transparency and management, the revision of Atlas data had created a new form of institutional authority that operated through systematic uncertainty rather than direct control. The effect was to undermine confidence in scientific databases while maintaining plausible deniability about the reasons for that erosion of trust. The question that haunted researchers who understood what was happening was not whether the data had been altered. That much was clear from the documented patterns of systematic revision. The question was whether those alterations served scientific accuracy or institutional convenience, whether they represented technical improvement or information management, whether they reflected commitment to truth or commitment to maintaining comfortable illusions about humanity's place in a cosmos that might be more complex and more populated than official sources were prepared to acknowledge. In the end, the distinction between cover-up and correction might be less important than the realization that both possibilities challenged fundamental assumptions about the independence of scientific research from external influences that operated according to criteria beyond the pursuit of knowledge and understanding. The systematic revision of Atlas data becomes less surprising when viewed against the broader historical context of how institutions have managed astronomical information that challenged established narratives or posed inconvenient questions about humanity's relationship with the cosmos. Throughout recorded history, the relationship between cosmic observations and institutional authority has followed patterns that reveal consistent tensions between discovery and control, between revelation and concealment. Ancient Chinese astronomical records provide perhaps the most extensively documented examples of systematic celestial information management. the imperial bureaucracy maintained elaborate astronomical observatories and employed professional astronomers whose primary responsibility was to monitor the heavens for signs that might reflect the stability or instability of dynastic rule. Comets, unusual planetary conjunctions, and unexpected celestial phenomena were interpreted as omens that could legitimize or challenge imperial authority. But the historical archives reveal systematic patterns of selective preservation and alteration in these astronomical records. Observations that supported the legitimacy of ruling dynasties were meticulously preserved in official chronicles, while phenomena that might be interpreted as negative portents were often omitted, minimized, or recontextualized in ways that neutralized their potentially destabilizing implications. The Tang dynasty astronomical records, spanning nearly 3 centuries from 618 to 907 CE, show clear evidence of this selective preservation. Bright comets that appeared during periods of imperial success were recorded with detailed descriptions of their paths, brightness, and duration. But similar phenomena that coincided with military defeats, natural disasters, or succession crises appear in the official chronicles as brief, ambiguous references that provide insufficient information for modern astronomical analysis. More significantly, comparison between official imperial records and surviving private astronomical diaries kept by scholar bureaucrats reveal systematic discrepancies in the documentation of the same celestial events. The personal records often describe phenomena that are completely absent from official archives, suggesting deliberate omission rather than observational failure. In other cases, the private diaries record brightness estimates, duration measurements, and positional data that differ substantially from the corresponding entries in imperial chronicles. The pattern indicates institutional mechanisms for managing astronomical information that operated according to political and social criteria rather than observational accuracy. Imperial astronomers were not simply recording what they observed in the sky. They were curating their observations according to principles that served dynastic stability and administrative convenience. Similar patterns appear in the astronomical records maintained by other civilizations that developed sophisticated observational capabilities. The Mayan codices that survive Spanish colonial destruction show evidence of systematic gaps in astronomical documentation that correlate with periods of political instability and cultural transformation. The detailed Venus tables that were maintained for centuries by Mayan astronomers suddenly become incomplete or erratic during periods when centralized authority was challenged by external invasion or internal conflict. The Babylonian astronomical diaries, among the most comprehensive and accurate ancient observational records, reveal more subtle but equally systematic patterns of information management. These cuneiform tablets, spanning nearly 8 centuries from 747 BCE to 61 BCE, document daily observations of planetary positions, lunar phases, and meteorological conditions with extraordinary precision and consistency. But statistical analysis of the surviving tablets reveals temporal gaps that correlate with periods of political upheaval and foreign occupation. The missing observations aren't randomly distributed across the centuries of record keeping. They cluster around specific historical periods when Babylonian independence was threatened by Assyrian, Persian, or Seleucid conquest. The gap suggests selective preservation that prioritized astronomical records from periods of stability while allowing documentation from turbulent eras to disappear. More troubling is evidence of systematic revision within the surviving tablets themselves. Comparative analysis of astronomical positions recorded in different copies of the same observational period reveals discrepancies that can't be explained by scribal errors or observational uncertainty. Some tablets appear to have been deliberately altered to bring recorded planetary positions into closer agreement with theoretical calculations, suggesting institutional pressure to conform observations to established mathematical models rather than preserve accurate documentation of what was actually observed in the sky. The Roman historical records provide examples of even more explicit astronomical information management. The imperial administration maintained professional astronomer priests whose responsibilities included monitoring celestial phenomena for signs that might affect state policy or public order. But the surviving accounts reveal systematic suppression of observations that might have generated public alarm or challenged imperial authority. Tacitus, Suetonius, and other Roman historians describe numerous instances where unusual celestial phenomena were observed by multiple witnesses, but were either omitted from official records or reinterpreted in ways that minimized their potential for generating social disruption. Bright comets were sometimes described as dim stars. Unusual planetary conjunctions were recontextualized as routine astronomical events. Solar eclipses that might have been interpreted as negative omens were presented in official accounts as anticipated phenomena that posed no threat to imperial stability. The mechanisms for implementing this information management were sophisticated and systematic. Imperial astronomers operated within administrative frameworks that required their observations to be reviewed by political authorities before publication or public dissemination. Astronomical phenomena that pose potential risks to public order could be classified as state secrets, accessible only to officials with appropriate security clearances. These Roman precedents are particularly relevant to contemporary concerns about astronomical data management because they established institutional procedures that have persisted, in modified forms, through subsequent historical periods. The concept that cosmic observations might pose risks to social stability and therefore require management by state authorities became embedded in European administrative tradition and was later exported to colonial territories around the world. During the medieval period, the Christian Church assumed responsibility for managing astronomical information that might challenge religious doctrine or generate popular unrest. The ecclesiastical authorities maintained astronomical observatories and employed professional astronomers, but their observations were subject to theological review that could result in suppression, alteration, or reinterpretation when they conflicted with established religious teachings. The most famous example of ecclesiastical astronomical censorship involves Galileo's telescopic observations of Jupiter's moons, Venus's phases, and lunar surface features. But the institutional mechanisms that enabled this censorship had been developed through centuries of managing less dramatic but equally systematic astronomical information that challenged geocentric cosmology or suggested that celestial phenomena operated according to natural laws rather than divine intervention. Church astronomical records from this period show patterns of selective preservation and systematic revision that parallel the techniques used by earlier imperial administrations. Observations that supported established theological frameworks were meticulously documented, while phenomena that posed challenges to religious doctrine were omitted, minimized, or recontextualized in ways that neutralized their potentially disruptive implications. The Renaissance and Enlightenment periods brought increased emphasis on observational accuracy and scientific objectivity, but institutional pressures for astronomical information management persisted in modified forms. Royal observatories were established throughout Europe, but they operated within political frameworks that required their discoveries to be reviewed by state authorities before public disclosure. The most significant example of this institutional control involves the systematic suppression of accurate measurements of Earth's size and shape that conflicted with political boundaries or territorial claims. Geodetic surveys conducted by royal astronomers often revealed geographical information that challenged existing maps or territorial assumptions, leading to classification of results or alteration of published measurements to avoid diplomatic complications. The transition to modern democratic institutions and professional scientific organizations reduced but didn't eliminate pressures for astronomical information management. The 20th century brought new categories of cosmic observations that intersected with national security interests, creating institutional frameworks for classifying or controlling astronomical discoveries that might have strategic implications. During World War II, observations of artificial satellites and unusual atmospheric phenomena were routinely classified by military authorities who determined whether public disclosure served broader strategic interests. Ground-based telescopes that detected previously unknown objects in Earth orbit found their discoveries subject to security review that could result in indefinite classification or systematic alteration of published characteristics. The Cold War period intensified these information management pressures, creating elaborate bureaucratic mechanisms for controlling astronomical information that might reveal military capabilities or suggest technological developments that could affect strategic balance. Observations of satellite activities, unusual radio emissions, and anomalous atmospheric phenomena were channeled through classification systems that effectively removed large categories of astronomical data from public accessibility. More significantly, the institutional frameworks developed during this period established precedents for managing astronomical information according to criteria that extended beyond simple national security concerns. Cosmic observations that might generate public alarm, challenge established scientific paradigms, or suggest technological capabilities beyond known human development became subject to review by authorities who operated according to undisclosed decision-making criteria. These historical precedents provide disturbing context for understanding the systematic revision of ATLAS data. The techniques used to alter the observational record, gradual adjustment of anomalous measurements, selective application of technical corrections, coordination across international boundaries, reflect information management methods that have been refined through centuries of institutional practice. The bureaucratic mechanisms that enabled these alterations, database management authorities with power to revise archived observations, technical explanations that obscured decision-making processes, administrative barriers that prevented independent verification, represent modern implementations of control systems that have been used throughout history to manage inconvenient astronomical discoveries. Most troubling is the realization that these information management techniques have become more sophisticated and less detectable over time. Ancient Chinese astronomers who omitted comets from imperial chronicles left obvious gaps in their records that modern scholars can identify and analyze. Contemporary database administrators who systematically revise archived observations can implement changes that appear to be routine technical improvements while serving institutional priorities that remain hidden from public scrutiny. The historical pattern suggests that institutional authority has always been uncomfortable with astronomical discoveries that challenge established narratives about humanity's place in the cosmos. When the sky speaks too loudly about possibilities that threaten social stability, scientific orthodoxy, or administrative convenience, the response has consistently been to manage the message rather than acknowledge the implications of what has been observed. In the case of 3i Atlas, the systematic data revisions may represent the latest iteration of information management techniques that have been applied to inconvenient cosmic observations throughout recorded history. The sophisticated coordination, subtle implementation, and bureaucratic justification of the alterations reflect institutional capabilities that have been developed through centuries of managing astronomical information according to criteria beyond simple scientific accuracy. The historical precedents don't prove that ATLAS data was deliberately manipulated for non-scientific reasons, but they demonstrate that such manipulation would be entirely consistent with documented patterns of institutional behavior when cosmic observations become inconvenient for authorities who determine what information is suitable for public consumption. The question is not whether institutions have the capability and precedent for managing astronomical information. The historical record clearly demonstrates both. The question is whether contemporary authorities have determined that ATLAS observations pose sufficient risks to public order, scientific orthodoxy, or institutional stability to justify implementing information management techniques that have been refined through millennia of institutional practice. In the gentle transformation of ATLAS measurements from anomalous to ordinary, from remarkable to unremarkable, we may be witnessing the latest chapter in a very ancient story about how human institutions respond when the cosmos reveals truths that challenge comfortable assumptions about our place in the vast darkness above our heads. In the quiet transformation of numbers that were supposed to represent permanent truth, we discover something profound about the nature of knowledge itself and the institutions we trust to preserve it. The systematic revision of ATLAS data, whether motivated by scientific correction or institutional convenience, reveals that even the most objective measurements our civilization can produce remain subject to forces that operate according to principles beyond simple accuracy or transparency. Data, we have learned, is not the neutral, immutable foundation of scientific understanding that we once believed it to be. Instead, it exists within networks of human authority, institutional priority, and social purpose that can transform measurements as surely as time transforms memory. The numbers that describe our cosmos are not just mathematical abstractions, they are social artifacts that reflect the values, fears, and intentions of the civilizations that create and preserve them. This realization carries implications that extend far beyond the specific case of 3i Atlas to encompass fundamental questions about how human societies construct and maintain their understanding of reality. If verified astronomical observations can be systematically altered without adequate justification or documentation, What does that mean for the reliability of any knowledge that depends on institutional preservation and transmission? The Atlas data revisions occurred within systems that had been specifically designed to prevent unauthorized alteration. International databases, peer review processes, and professional oversight mechanisms were supposed to create multiple layers of verification that would make systematic manipulation impossible, or at least immediately detectable. Yet something reached through all these safeguards and touched the observational record with invisible hands, transforming verified measurements in ways that served purposes we can only speculate about. This breach of supposedly secure knowledge systems suggests vulnerabilities in how human societies preserve and transmit information that may be more extensive than we have acknowledged. The institutional frameworks that protect scientific knowledge from corruption or manipulation may be less robust than their architects assumed, particularly when the knowledge they preserve intersects with interests that operate according to criteria beyond simple scientific accuracy. The psychological dimensions of this discovery are perhaps more significant than the technical aspects of database security or information management. We have built our technological civilization on the assumption that certain types of knowledge, particularly scientific measurements of physical phenomena, exist in realms that are insulated from the social and political forces that might influence other categories of information. The systematic alteration of astronomical data challenges this assumption in ways that undermine confidence not just in specific databases, but in the entire framework of institutional authority that modern societies depend upon for their understanding of reality. When researchers discovered that their private records no longer matched authoritative databases, they were forced to confront the possibility that the most trusted sources of scientific information might be less reliable than their own personal observations. This inversion of authority, where individual memory becomes more trustworthy than institutional archives, represents a fundamental shift in the epistemological foundations of scientific knowledge. The response to this crisis of institutional credibility has followed predictable patterns. Most researchers have chosen to trust official explanations rather than acknowledge the possibility that systematic manipulation might have occurred. The psychological pressure to maintain confidence in established authority structures is so strong that it becomes easier to doubt personal observations, question individual memory, or assume technical ignorance rather than confront the implications of institutional unreliability. This psychological dynamic serves institutional interest by creating self-reinforcing cycles of doubt and deference. Researchers who notice discrepancies in archived data are encouraged to assume personal error rather than challenge official accounts. The effect is to isolate potential critics from each other while maintaining the appearance of broad professional consensus around the reliability of institutional data management. But the psychological costs of this dynamic extend beyond simple deference to authority. When individuals are systematically encouraged to trust institutional accounts over their own observations, they gradually lose confidence in to distinguish between reliable and unreliable information. The effect is to create populations that are increasingly dependent on official sources for their understanding of reality, even when those sources demonstrate characteristics that should trigger skepticism rather than trust. The historical patterns we have examined reveal that this dynamic is not accidental, but represents the predictable outcome of information management techniques that have been refined through centuries of institutional practice. When authorities determine that certain types of knowledge pose risks to social stability or institutional convenience, the standard response is not direct suppression, but subtle manipulation that gradually transforms inconvenient observations into acceptable narratives. The sophistication of these techniques has increased dramatically with the development of digital information systems that allow real-time alteration of archived data without leaving obvious traces of modification. Unlike physical documents that show clear evidence of erasure or revision, electronic databases can be updated seamlessly in ways that make the original versions disappear completely from accessible records. This technological capability creates new categories of vulnerability that previous generations of scholars and researchers never had to consider. The permanence that once characterized written records has been replaced by malleability that makes any digitally preserved information subject to retroactive revision. The effect is to transform human knowledge from a cumulative, stable foundation into something more fluid and contingent. subject to continuous reinterpretation according to criteria that may not be openly acknowledged. The implications for scientific progress are staggering. If researchers cannot trust that archived data will remain stable and accessible, how can they build upon previous work or verify published results? If institutional databases can be systematically altered without adequate documentation, how can the scientific community maintain confidence in the cumulative nature of knowledge that has been the foundation of technological advancement for centuries? The Atlas data revisions may represent a preview of what scientific research looks like in an era where information preservation is controlled by authorities who operate according to undisclosed criteria. Rather than building upon stable foundations of verified observation, researchers may find themselves working with data sets that are continuously evolving according to institutional priorities that remain hidden from public scrutiny. This transformation would represent a fundamental shift from science as an objective investigation of natural phenomena to science as a managed presentation of information deemed suitable for public consumption. The distinction between discovery and disclosure would become increasingly significant, with institutional gatekeepers determining which aspects of cosmic reality are appropriate for broader awareness and which require management or concealment. The specific case of astronomical research adds particular urgency to these concerns because cosmic observations have unique potential to challenge anthropocentric assumptions about humanity's place in the universe. Discoveries that suggest the existence of advanced intelligence, unusual phenomena that can't be explained by conventional physics, or evidence of technological capabilities that exceed known human development all pose potential risks to social stability and institutional authority that might justify information management according to the historical patterns we have examined. The systematic revision of Atlas data may reflect institutional recognition that certain types of astronomical discoveries require careful management rather than simple disclosure. If our interstellar visitor exhibited characteristics that challenged established scientific paradigms or suggested possibilities that authorities determined were unsuitable for public awareness, the gradual transformation of anomalous measurements into ordinary ones would represent a sophisticated response that preserves institutional credibility while managing potentially disruptive information. This possibility transforms our understanding of what scientific databases represent. Rather than neutral repositories of objective measurements, they may function as carefully curated presentations of cosmic reality that serve institutional purposes beyond simple accuracy or completeness. The numbers that describe our universe may reflect not just what has been observed in the sky, but what has been deemed appropriate for preservation and transmission through systems controlled by authorities with undisclosed priorities. The philosophical implications of this realization extend to fundamental questions about the nature of truth and the possibility of objective knowledge in societies where information preservation is controlled by institutional hierarchies. If the most basic measurements of physical phenomena can be systematically altered without adequate justification, what confidence can we maintain in any institutionally mediated knowledge about the nature of reality? This question becomes particularly acute when we consider that most of what we believe about the cosmos comes not from direct personal observation, but from archived data that has been collected, processed, and preserved by institutional systems that we may not fully understand or trust. The vast majority of humanity has never independently verified the measurements that form the basis for our understanding of stellar distances, planetary compositions, or galactic structures. We accept these measurements because we trust the institutions that preserve them. But what happens when that trust is revealed to be misplaced? The erosion of confidence in institutional data management may force a return to more direct personal forms of knowledge acquisition. Rather than depending on official databases for their understanding of cosmic phenomena, researchers may need to develop independent observational capabilities that allow them to verify institutional claims through direct measurement and personal experience. This shift toward decentralized verification would represent a fundamental change in how scientific knowledge is constructed and validated. Instead of relying on institutional authority to determine what observations are accurate and reliable, individual researchers would bear greater responsibility for establishing the credibility of their source materials through independent confirmation and cross-verification. The technological tools for implementing this decentralized approach already exist. Digital communication networks allow researchers to share observations and compare measurements without depending on centralized databases. Affordable telescopic equipment makes independent astronomical observation accessible to broader populations. Open-source data analysis software provides alternatives to proprietary systems that might be subject to institutional control or manipulation, but the transition to more decentralized knowledge systems would require significant changes in how scientific communities organize themselves and evaluate the credibility of research claims. The efficiency and coordination that centralized databases provide would be lost, replaced by more labor-intensive but potentially more reliable systems based on independent verification and peer networking. The choice between institutional efficiency and knowledge reliability represents a fundamental tension that extends beyond astronomy to encompass broader questions about how democratic societies should organize their relationship with expert knowledge and scientific authority. The systematic revision of Atlas data may force recognition that these two objectives, institutional efficiency and knowledge reliability, are not always compatible, and that societies may need to choose between them. In the gentle transformation of cosmic measurements from anomalous to ordinary, from remarkable to unremarkable, we glimpse the possibility that our understanding of the universe is more malleable and more subject to institutional management than we have acknowledged. The numbers that describe our cosmic environment may reflect not just what exists in the darkness above our heads, but what institutions have determined it is appropriate for us to believe exist there. The meaning of the Atlas data revisions may ultimately lie not in what they reveal about our interstellar visitor, but in what they suggest about the systems we trust to preserve and transmit knowledge about the cosmos we inhabit. In the space between what was originally observed and what appears in contemporary databases, we discover questions about truth, authority, and the possibility of reliable knowledge that extend far beyond the specific case of any single cosmic object. Perhaps the real revelation is not what Atlas showed us about the universe, but what its changing data revealed about the institutions that stand between human observation and human understanding of the vast, mysterious, and potentially populated darkness that surrounds our small world. In the quiet revision of numbers that should never change, we have discovered that even truth itself can be edited when it becomes inconvenient for those who hold the pen that writes the official record of humanity's encounter with the infinite possibilities that exist in the space between the stars. The question that remains as 3i Atlas disappears into the cosmic distance is not what our databases say about our visitor, but whether those databases can be trusted to preserve accurate records of what we actually observed during its passage through our small corner of the galaxy. And in that question lies the possibility that we have learned something far more important about our own civilization than we ever learned about the mysterious object that prompted us to examine how we construct and preserve our knowledge of the cosmos above our heads.